Here we go. Let's find some characteristics of rational functions. This can sometimes be like a whole process, but just go one piece at a time. I like to start with the horizontal asymptote. With the horizontal asymptote, we have to think about how the function is going to be growing as x approaches infinity. So as x gets super, super huge, what's going to happen to the function? Where is it going to go? Is it going to positive infinity, negative infinity, or is it going to flatten out and approach one singular value? And if our function flattens out, that means we're going to have a horizontal asymptote. So to figure that out, we have to look at how the function's growing. I like to play a game of what's growing faster. So looking at the numerator. In terms of this x squared, x to the first, and 12, well, what's growing fastest is definitely that x squared. So this doesn't matter and this doesn't matter. So 2x squared, well, that's going to take over because that's going to be growing the fastest. In the denominator, well, if I had $3 billion minus 12, well, that minus 12 doesn't really matter, so we can get rid of that. And what's growing the fastest is that 3x. Now that I just have this fraction, well, we can cancel out one of the x's, and we're left with 2x over 3. Well, if x gets really, really big, we're plugging in a million, a billion, a trillion. This is going to keep growing and growing with that. So it's going to go off to positive infinity and then go x approaches negative infinity, y will approach negative infinity. So horizontal asymptote in this case, we don't have one. And that will always be the case if the power in the numerator is bigger than the power in the denominator, right? The numerator is growing faster, so it'll always get bigger and bigger and bigger and bigger. Probably shouldn't have marked all that up. Anyway, so horizontal asymptote, we said there was none. Now we have to look at vertical asymptotes. Vertical asymptotes are going to happen when we're dividing by 0, right? That's also where a hole can happen in the function. So to know where we're dividing by 0, well, the best course of action would be to factor. Denominators can factor super easily. We just got to take out a greatest common factor of 3, and we're left with x minus 4. In the numerator, looks like we're going to have to do some factor by grouping because we have a coefficient, a leading coefficient that's bigger than 1. I like to use the x method. And if you still don't know how to factor by grouping, you better check out my other video. Okay, you know who you are. No more guessing checking out here. Anyway, we're going to multiply to get a times c. So 2 times negative 12, negative 24, and add to get negative 5. Go through our options, 10 and 2, 6 and 4, 3 and 8. Negative 8 plus 3, that works. So we go back, plug it into our numerator. Keeping the first term, just rewriting that middle term. Plus 3x minus 24. Sorry, I'm going into so much detail about factoring by grouping. I'm very passionate about it. Anyway, group it, group it, group it, group it. Take out a greatest common factor from that first part, taking out a 2x, left with x minus 4. Take out a 3 from the second one, we're left with x minus 4. Both of them have an x minus 4, so let's bring it out front. X minus 4 times the leftovers, 2x plus 3. All over 3 times x minus 4. Ta-da! Now we can clearly see that we have a point of discontinuity if I were to plug in 4 for x. That would be bad. We do not want to divide by 0. So I can't plug in 4 for x, so that tells us about our domain. Our domain is from negative infinity up until 4. I can plug in any number, just not 4 itself. But I can also pick right back up just after 4 and go all the way to infinity and not have any problems. So since I can't plug in 4 for x. That means we either have a hole or we have a vertical asymptote. I know this is a hole because I'm able to remove this x minus 4, right? Removable discontinuity. So that means we're going to have a hole at x equals 4. All right, the range, well, we already mentioned that there's no horizontal asymptote. So if we were to plug in a really big negative number, then the function would go down to negative infinity. If we were to plug in a really big positive number, the function would approach positive infinity. Vertical asymptotes, well, there's no other spots where we're dividing by 0. It's just that x minus 4 spot. And I'm not going to have a hole and a vertical asymptote at the same spot, so none for that one too. In order to find the y-intercepts, well, that is when y equals 0, right? Y-intercepts, no. Y-intercepts when x equals 0, because we're not moving to the left or right, so we're crossing the y-axis. So when x equals 0, if I plug in 0 there and 0 there and 0 there, we would end up with negative 12 over negative 12. So our y-intercept is at 0, 1. The x-intercept, that one's when y equals 0. So I like to use our factored version here. And I don't care about where the denominator equals 0 because we just mentioned that's bad, right? So we're only looking at where the numerator equals 0. Because if the numerator of a fraction equals 0, well, then the whole thing equals 0. So I care about when x minus 4 times 2x plus 3 equals 0. And then you split it up. And you split it up. So that means x equals 4 and x equals negative 3 over 2. But do not write this down as an answer. Because what happens when you plug in 4? Divide by 0. So we only have one x-intercept. We're going to cross over the x-axis there, but not touch it, right? Because we're jumping over that hole. So x-intercept, the only one is at negative 3 over 2, 0. Oh, that was so fun.